Okay, we talked about entropy, and now I want to look at entropy change for ideal gases, entropy balance for reversible processes, and entropy balance for irreversible processes. Entropy change for an ideal gas. I think we've shown earlier that, or you can show that ds is Cp over T dt minus R over molecular weight divided by P dP. This all comes from adding heat to a reversible process, and we developed the fundamental property equation, applied that to ideal gas, came up with this above equation. If we integrate that at constant Cp, take Cp outside and integrate, you get a log function. So S2 minus S1 depends on the logs of the temperature ratio and the pressure ratio. In the case where S2 equals S1, we call that an isentropic process. Out of your entropy balance, that'll often happen when the process is reversible, S generated is 0, and adiabatic, no S added by heat, or no entropy added by heat, are removed. And solve this equation. A little algebra leads you to these equations, and I suggest that you slow down, stop, and prove each one of these starting from the top equation. Take the algebra to the next step. And we have, for an isentropic ideal gas with a constant Cp, the following equation. T2 over T1 equals P2 over P1 to the R over molecular weight divided by Cp. With a little more manipulation, we can show that this exponent we're raising it all to depends only on Cp/Cv. Recall that Cp minus Cv is R over molecular weight. Then we define this K, and this is commonly done in thermo for ideal gas situations, where K is the ratio of the constant pressure heat capacity to the constant volume heat capacity. And so this exponent becomes K minus 1 over K. The entropy of an ideal gas as a function of T and V, then, is also, we've done this before, ds is Cv over T dt plus R over molecular weight dV over V. Integrating at constant Cv yields this equation. And again, I suggest you stop and prove that. In the case where we have an isentropic process, where that's reversible and adiabatic will lead to an isentropic process, very similar manipulations, so I'm going to click right through them. And I'd like you to again pause and develop each of these equations algebraically. It's simple algebra. And we lead to the following relationship. And these relationships are awfully handy when you're dealing with ideal processes where they could be considered close to reversible. T2 over T1 is the ratio of V1 over V2 to this exponent. And again, some manipulation on the exponent leads to K minus 1, where again, K is this ratio of Cp to Cv. Now, for an isentropic ideal gas at constant Cp, Cv, which would be constant K also, T2 equals T1, P2 over P1 to the K minus 1 over K. Or T2 equals T1, V1 over V2 to the K minus 1. Typically, I'll use this equation when I'm looking at turbines or compressors, steady flow processes where the pressure ratio is known, and I'll use the second aspect to find outlet temperatures or final temperatures in piston cylinder type processes where you know the ratio of V1 to V2. By the way, in piston cylinder processes, this is called the compression ratio, whereas P2 over P1 is often called the pressure ratio for turbines and compressor systems. We can also find that this satisfies a polytropic process, which is PV to the K is constant, so P2 over P1 equals V1 over V2 to the K, which you get from the above equation. Now, for modeling reversible processes, what do we know about reversible processes? That S generated is equal to 0. So sometimes that's called sigma dot. I call it S generated with a dot over it being per time. This sets the best case situation. So a reversible process is always the best you can do. You never quite reach it, but it's the best case we could do. So when you hear the word maximum or minimum, you're thinking, S generated is approaching 0. So example, a reversible adiabatic turbine receives air at 900 K and 10 bars and discharges to 1 bar. I want to find the outlet temperature and that the work that's done per mass for this turbine. So here's a sketch of our system. Air coming in at 900 K and high pressure. It's adiabatic. We've insulated it. Got a lot of insulation around this thing. So Q equals 0. Taking work out, and air is discharged usually to the atmosphere at about 1 bar, and we don't know the temperature, but we know it's reversible. We know it's adiabatic, and we can do the energy balance on it and the entropy balance, and we can find the outlet temperature and the work done. So first, the entropy balance. MS1 plus S generated equals MS2. So, of course, if it's reversible, S generated equals 0. Why is there nothing accumulated? In equals out. Nothing accumulated. We're assuming that it is at steady state. And if it's steady state, the accumulation term goes to 0. There's no increase or decrease of the entropy in the system. Just what goes in, goes out. Steady state. That's our entropy balance. So S2 minus S1 equals 0. We have an isentropic process. Again, the same integrals we just did. Leads to, with constant Cp, T2 equals T1, P2 over P1, 900 times 1 over 10 to this exponent, K minus 1 over K. And for T average of 700 degrees, we found that the Cp for air, I'm sorry, this exponent, I said K minus 1 over K, that's really R over Cp. I'm sorry, R over the molecular weight of air. Molecular weight of air is 29 divided by Cp. We're taking this Cp for the average process temperature to be, assuming an average process temperature of 700, Cp is about 1.075. That's kilojoules per kilogram K. And we could also find the K, Cp over Cv, and solve it that way. When we do this equation, we find that T equals 487 Kelvin. And coming in at 900 down to 487, that's close to 500. So our assumption of T average of 700 wasn't too far off. Again, stop, take a moment, reproduce all this on your calculator, on paper. Make sure you can get to these steps here, through these steps here. Okay, suppose I took that turbine. With the ideal turbine, we found that the outlet temperature was 487. Suppose I measured the temperature of the turbine and found it was really 530. Now suppose it was still very well insulated. How did that happen? Well, what happened was that there was friction. It wasn't truly reversible. Maybe there was friction with the side of the turbine, friction in the rotor, friction of the gas as it hit the blades, any kind of friction, and that was turned into thermal energy, which wound up going back into the gas. So instead of dropping, taking all the energy out at work, some of the energy went into heat, which went into the gas itself. So it didn't drop as far as 487. It only dropped in temperature down to 530. Remember, you're going into the turbine at 900. Because you're taking work out, the temperature drops. And it would drop to 487 if we did it perfectly. But here it's not dropping, only to 530. Now the question, well, it's not isentropic anymore. So how much entropy was generated per kilogram? Now I can take the turbine as a system, still assuming adiabatic, and now calculate the entropy generated, which would be the entropy out minus the entropy in if I do it on a per mass basis. S generated equals S2 minus S1. And again, assuming constant Cp, integrate it, and I get this equation for delta S, or S generated. Actually, that's delta S, S2 minus S1, which in this case, from our entropy balance, is S generated. Solve that, and we come up with, plug in the numbers, come up with S generated equals 0.0909 kilojoules per kilogram K. If I ever came up with a negative number for S generated, then I did something wrong, or there's something wrong with the problem statement, because you can never have a process where S generated is negative. So let's calculate the work done. H in minus H out per mass, because it's adiabatic. Do the energy balance, you should get this. Reversible turbine, we got 444 kilojoules per kilogram. But in the irreversible turbine, where we had the S generated and it came out at 530, you see we didn't get as much work. We lost the opportunity really to produce another 45 kilojoules per kilogram of work. That's what we would have had it been reversible. Actually, we haven't lost all that. The fluid coming out of the turbine is a little bit hotter in the second case, in the irreversible turbine, so there is a way to get a little bit of that back, but not much. A little bit of that so-called lost work. An adiabatic, let's take another example, this time with a piston cylinder. See, we have an adiabatic piston cylinder arrangement. Again, adiabatic, Q is 0. Undergoes a reversible expansion to 10 times its original volume. If the cylinder contains air at 900, start with the same temperature as we did with the turbine. What is the final temperature? Here's our system. We're taking work out as the piston expands, as the piston goes up. Entropy balance, in plus generated equals out plus accumulated. Now we're doing, there is an accumulation, as you can see, because this is not a steady state process. It starts at state 1, state 2. The system properties have changed as the piston goes to a higher level. There was nothing coming in because there was no heat. It was adiabatic. Nothing generated because it was reversible. Nothing out because the work is going out, but in the entropy balance, work carries no entropy. So it is 0. So the accumulated term is all that left, and it must equal 0. So the accumulated term is the mass times S final minus S initial, which tells us S final equals S initial. Here we have a reversible adiabatic process, and the result is delta S equals 0. So, plugging that in, we have, again, we developed this earlier, and assuming a constant CV of 0.788. Now, you see CV is less than CP, remember. CV is equal to CP minus R over molecular weight. Comes out to 0.788. Plugging all that in, we get T final equals T initial times V initial over V final to the R over molecular weight, divided by CV. This results in a final temperature of 389.4 Kelvin. So it dropped all the way down from 900 all the way down to 389. The work done in this case is U initial minus U final. Plug in the energy balance and you'll find that the work per mass, I'm using a small w for work per mass, is a specific initial energy minus a specific final internal energy. And again, for an ideal gas, That's CV times delta T, T initial minus T final, or minus delta T as the case may be. And that turns out to the workout is equal to 402 kilojoules per kilogram, expanding that gas. So, entropy changes for an ideal gas we've looked at and found that ds is a function of the T and P, or a function of T and V, or you could treat it as a function of V and P, but usually you're using one of the first two. If we have an isentropic process, then we can find the final temperature as a function of the change in pressure or as a function of the change in volume. And you could do it either way, but usually it's more convenient with flowing processes to express as a function of pressure, and with piston cylinder type arrangements as a function of the volume. We did entropy balances for reversible processes. In this case, S generated is 0. And if it's adiabatic, Q over T is 0. And that allows us to come up with the result that is isentropic when it's reversible, both reversible and adiabatic. We looked at irreversible processes where the S generated is calculated always a positive number. And you should know that S generated, the higher it is, the more irreversible the process, the more inefficient the process is. So if you're looking at two processes side by side, you want to compare them, then the greater the S generated, the more irreversible the process is going to be, less efficient. The potential is to do work is lost due to dissipation. When we looked at that turbine problem, the entropy was generated in the irreversible case, and the friction went into dissipation, meaning it was turned into a thermal type energy, which is not easy to get the work back out. In fact, it's impossible to get all the work back out of the energy once it's dissipated into a thermal form. So for homework, what I'd like you to do is finish reading Chapter 7, and I'll put some problems in either Blackboard or Moodle, whichever you can access. Okay.